In this video, we're going to look at examples of working with the energy levels of the hydrogen atom. We're going to find frequencies, we're going to find wavelengths, we'll find energies, we'll find what state it was in, lots of examples. I'm going to begin by just pulling this up again and pointing out, the visibles all fall from something higher, 3 through 6 energy levels, and fall to energy level 2. Anything that falls back down to the ground state here are going to be in the UV, and if they fall to level 3, it's going to be in the IR. Okay, so example number 1. How energetic is an electron in the 9th excited state? Oop. Didn't mean to click there. Not exactly sure even how I clicked there. Okay, the first thing you have to remember is that the ground state is by definition n equals 1. So the 9th excited state actually means n equals 10. Okay? So how energetic is an electron in this state? So the 10 here means you're in n equals 10. So that's negative 13.6 eV divided by 10 squared, which is negative 13.6 eV divided by 100, which is negative 0.136 eV. Example 2. What is the frequency of the photon emitted when an electron falls from n equals 3 to n equals 2? So frequency, remember, was HF equals E final minus E initial. Because it's a photon emitted, in the way we're doing things, that means the frequency is going to be negative. So don't be surprised when we get a number out that is negative. Okay. So what are our two energies? E final occurs when n equals n equals 2. So that's negative 13.6 eV divided by 2 squared. And if you look at the front chart or plug that into your calculator, you get negative 3.4 eV. E initial occurs when n equals 3, so that's negative 13.6 eV divided by 3 squared, which is negative 1.51 eV. So now we just plug in numbers, negative 3.4 minus a negative 1.51 frequency, and then remember H in EV units is 4.14 times 10 to the negative 15. And this guy has units of EV times seconds. So F is going to equal negative 3.4 plus 1.51 all divided by 4.14 times 10 to the minus 15. And when you put that all into your calculator, you get 4.6 times 10 to the 14, not joules, sorry, 1 over seconds, but 1 over seconds by definition is hertz. Ooh, I kind of missed there. Okay, so remember that's 4.6 times 10 to the 14th hertz. Example 3. What is the wavelength of the photon emitted when an electron falls from n equals 5 to n equals 2? To do this, we use this formula. N final squared minus. Okay. The Rydberg constant is by definition 1.097 times 10 to the 7th with units of 1 over meters. 1 over n final is going to be 1 over 2 squared minus 1 over 5 squared. Okay. So when you put that all into your calculator, you get 2.30 times 10 to the 6th, 1 over meters, and that equals 1 over the wavelength. So the wavelength is the inverse of that, which is 4.34 times 10 to the minus 7 meters, or equivalent 434 nanometers. And this is the photon that is in the deep purple that maybe you might be able to see. Our fourth example, how much energy is lost when the electron falls from n equals 4 to n equals 2? To do this, you just need to subtract. So E final minus E initial is going to be negative 13.6 over 2 squared minus negative 13.6 over 4 squared, which turns out to be negative 2.55 eV. And it's hopefully not too surprising that it's negative because the electron lost energy. And for fifth and final example, you are told you have an electron that is falling from an excited level down to the ground state, and I give you the frequency. You want to know where did it start, so you're looking to find n. Since we're given frequency, let's use this formula. Okay. We need to keep in mind we are releasing a photon. So again, we need to make sure that we plug this in as a negative number because the electron is losing energy. Okay, so H is 4.14 times 10 to the negative 15. Our frequency is going to be a negative 2.92 times 10 to the, that should be a plus 15. Sorry, I typed it in wrong. Plus 15. And that's going to equal negative 13.6 over n final squared, but it's going to the ground state. And by the definition, the ground state is n equals 1. So this is negative 13.6 over 1 squared minus negative 13.6 over n initial squared. When you multiply the left-hand side together, you get negative 12.08, and that has to equal negative 13.6 times 1 minus 1 over n initial squared. So now I can divide both sides by negative 13.6, and that results in 0.88 equals 1 minus 1 over n initial squared. I now need to subtract 1 from both sides, which gives me negative 1.2 equals negative 1 over n initial squared. Okay. I'm going to take this, I'm going to get rid of the negative signs because I have negative signs on both sides, so they cancel. We can make them positive. I'm now going to take the square root. The square root of 1.6 is 0.346, and that equals 1 over n initial, which means n initial has to be something like 2.88. But our quantum numbers cannot be non-integer. Okay, so why is it? Well, it's round-off error. If you had to guess, would it be 2 or would it be 3? I hope you all can think here that this actually is meaning that the starting state was n equals 3.